Well, so your question is specifically, let me put it with the diagram. So what we are saying here is that we have phi in at the input with the phase error detector with a certain gain KPD, followed by loop filter, and then the VCO, which also has the transfer function of K VCO over S, right? So it's like this. This is your phi out, and by the way, this is something which is fed back. Where is phi error? Phi error is here, isn't it? So now when you applied a frequency step, you said that delta omega in is equal to delta omega 0 of u of t. You applied a frequency step. So what will be the phase step for this? If your frequency step is like this, phase step will be delta omega in times dt, integral, right? Which is going to be integral of delta omega of 0 times dt starting from t0 to t. So you see here that you have the input phase changing like this. Is it correct? Yeah. So now if input phase changes like this, what is the value of input phase at t tends to infinity? It is going to be infinity, right? So if your output phase tracks input phase after some time, let us say, then phi out of t is going to be equal to delta phi in of t. If that happens, then I think you will have no problem in telling that the phase error or the change in the phase error is going to be 0. Am I correct? No. Does this solve your doubt? Or what you are thinking? Tell me. Yeah, we could say that, and we will observe that it is reality. It is not something just we say. Okay. If input and output are, if output is tracking your input, then the error which is going inside the loop is 0, isn't it? So that is what we were talking that, okay, so let me just work that out, if for benefit of others also. So what we have is delta phi out by delta phi in of S, right? This transfer function was loop gain by 1 plus loop gain, right? And then delta phi error of S with respect to delta phi in of S, this is going to be 1 by 1 plus loop gain, correct? So if you are looking at delta phi out of t at limit t tends to infinity, this was for the step input, step frequency input, this was S times delta omega of 0 by S square into 1 by 1 plus 1 by loop gain. Sorry, yeah. So this is going to be 1 by loop gain, and loop gain was KPD, right? F of S times LF of S times K VCO by S. This was the case? Okay. And here if we substitute, here we are finding the value as t tends to infinity. If we substitute, we will find that this value goes to infinity. Is that correct? Yes. Now the other thing which we are saying is with respect to error. So delta phi error of t, limit s tends to 0, s times delta omega 0 by s square, right? And this is 1 by 1 plus loop gain, which is kpd, loop filter of s times kvco divided by s, right? So for the same change in the frequency, we see that this cancels out, right? And s multiplies inside, so you are going to, this will cancel out, this goes away. So what you are having is, if I just look at it, delta omega of 0 divided by kpd times loop filter of 0 times kvco. Is this correct? Okay, this is the value as t tends to infinity. We told that if we want this particular phase error to be 0, it is not 0 for all cases. If we want it to be 0, then it should be, loop filter should have infinite gain at DC. Okay, so loop filter of 0 should tend to infinity, and then only we can have phase error as 0. It will not become immediately 0, it will take some time. Okay, how much time? It depends on the loop filter. Is that okay? Okay. Any other question? Okay. So at the very end of the class, we were discussing, I think some people left, so let me just talk about it. So at the end, we applied a frequency ramp, not step. So we applied delta omega 0 times, or you can change the units and so on. It was just increasing. So delta omega dash you can say, otherwise you will say units are not correct. So it was like this, right? So for this, the phase error as t tends to infinity turns out to be limit of s tends to 0, s times delta omega dash 0 divided by s cube into 1 plus 1 by kpd times loop filter of s into kvco by s here. Okay, so in the last class we made one error just while substituting the values. So this will be s square. So s square goes inside, this becomes s square, and then this goes away, and you are also going to have s here. Okay, so this is what your final value is going to be. So if you look at it, if loop filter of 0 happens to be, so let me just write it, this value is going to be, I substitute s equals 0, right? So it is going to be 0 plus, this is a 0 value by the way, it is s here, or let me just write it as rather than make it 0, limit s tends to 0 times, okay, kpd times loop filter of 0 times kvco. Right? So if loop filter of 0 is equal to 1, then surely your error is going to be infinity. But if loop filter of 0 is 1 by s, then you will have some finite phase error. And if loop filter of 0 is equal to 1 by s square, right, of that kind of term, then you will have phase error will go to 0. So the number of integrators which you would like to have, or 1 over s, in the loop filter, it depends on, or you can say that if I want to track just a step change in the frequency or a small change in the frequency, it's fair enough that okay, I use one integrator in the loop filter, but if I want to track the frequency, continuously changing frequency, I need to have more integrators in the loop filter. Okay. So a lot depends on the loop filter. And by the way, someone at the end of the class also mentioned that why don't we use loop filter as a low pass filter. Well, you can use loop filter as a low pass filter like a DC with a DC gain into 1 plus S by omega p. If this happens to be a loop filter, then just consider the different cases where your input phase step phi in of t is equal to delta phi in of 0 times u of t. In this particular case, delta phi error of t as t tends to infinity, right? This is going to be equal to delta phi in of 0. And what we are doing here is we are looking at loop filter when we are looking at for the loop filter value when we are applying a phase step, right? So what we are going to have here is, you will see that one particular S cancels out and you will have 1 plus 0 divided by kpd into loop filter of 0 times kvco. Sorry, this is not the case. It should be other way around. This is going to be 1 plus kpd times loop filter of 0 times kvco divided by s or 0. Right? So if you have a 0 here, then this term goes to infinity. Okay, and then you are going to have phase error will be 0. So phase is going to be tracked if you have a DC gain. Now if you apply, in place of that, if you apply a frequency change, phi n of t is delta omega in 0 times u of t, then you are going to have a phase error which will depend on the DC gain of the loop filter. Okay, and that is going to be delta omega in of 0 plus, here you are going to get 0 plus kpd times loop filter of 0 times kvco. The s in the denominator will also be cancelled out, right? And loop filter of 0 value is going to be a DC, so larger the DC gain, lower will be the frequency error. Okay, it will, yes. Right. Yes. Yeah, so the whole thing is I am not that particular about just a delta phi error. I am very much concerned about the absolute value of phi error. Okay, so let us say if you keep on changing this delta, right? So if the delta phi error turns out to be a large value, how much large value can you have in your system? Looking at the PLL, if you go back, you know this particular phase error detector is implemented by using a mixer, right? And the output, see, when we are just doing this small signal analysis, it tells us one particular thing, that V error is kpd times phase error. Right, whether you want to change in delta V or delta phi error, whichever way you want to look at it. Now, this is a linear system where it says if you keep on increasing the phase error by a large value, your V error will also change. Right? But we know that there are hard limits on V error because the way the phase error detector is implemented. right? Yeah, so just listen to this. So the thing is, we cannot have that large change in the phase error. Do you agree to that? We cannot have a large change in the phase error, or no? Yeah. So if you cannot have a large change in the phase error, if the phase error is equal to 0 all the time or remains 0 all the time, then it will be a really good situation. At least looking at it, quantitatively we will see it later. Okay, does that answer your question? There are two things. When you say delta phi n is particularly just because of some random noise, it will change in both the directions, agreed. But that noise is not, mostly that noise is not going to take you out of this law. Okay, that noise is pretty small. When we are talking about this phase of frequency step, this is like modulating. This is like you want to change the phase particularly. Okay, that random noise is the disturbance which you are talking about, plus minus, those variations are quite small, and we would never like to make our phase error equal to 0 for each and every small disturbance which is going to happen. We can't make that. Okay, so that will not happen. Yeah, this is particularly for changes in the input which are normally tried with the modulation of the PLL output. Or because of some reason the clock gets delayed or the clock shifts or so on, is for that. It is like this. See, if the system is stable, any small disturbance should not make it unstable, right? So what we look at it, how large disturbance can you give to the system without driving the system out of stable operation. Okay, if it turns out to be that we apply some particular frequency step and then the phase error tends to infinity, that only means that you are going out of clock. You cannot have an infinite phase error here. Yeah, so it is like that. Okay, any other question? Okay, so what we concluded the other day and from today's analysis also, that this loop filter particularly plays a very important role in making your phase error or phase error 0 or track the input phase, track the input frequency ramp and so on. Okay, so based on this loop filter only, the PLL are characterized with different PLL are characterized as having different types and different order. So let me just say you have a loop filter with the numerator written in terms of in Laplace domain and denominator also in Laplace domain. Your loop gain of the PLL, the block diagram which is shown in the previous page, is going to be KPD times loop filter of S times KVCO by S. Okay, now there are two things which are defined. One is type of PLL, okay, and this is defined as number of integrators in the PLL loop. Okay, so what is an integrator? Integrator has a transfer function. So let me just write it. Integrator has transfer function as 1 over S, right? So you look at how many 1 over S you are having in the PLL and you will know what is the type of the PLL. Second thing is order of PLL. Okay, an order of PLL is defined as number of poles in the PLL loop, okay, in the loop gain you can say. And you see, every integrator comes with a pole, but every pole does not come with an integrator. Okay, that should be clear. So now let me just pick up a couple of options. So if I have loop filter of S, let us say 1 or some particular low pass filter which is a DC gain plus a pole, right? Then an integrator and a 0, 1 plus S by omega Z1 or omega Z, let us say, divided by S, and then another one may be 1 plus S by omega Z1 into 1 plus S by omega Z2. This is just the transfer function of the loop filter. Okay, and I need to define what is type and order. So when your loop filter is 1, there is only one integrator in the loop which is coming because of the VCO, right? So type is 1 and order is also 1. When you have a loop filter as a low pass filter, which you see here a DC gain, in that case your type still remains 1 because you have only VCO's integrator, but the order increases to 2. One pole is at S equals to 0, right? Another pole is at S equals omega p. When you have this loop filter here with a 0 and an integrator, your order is 2, okay, and your pole is also 2. 2 poles at 0. When you have the third one, then you are having 3 integrators, so it becomes type 3 and order 3. Okay, by the way, you can have type 2 order 3. Let us say if this has another pole 1 plus S omega p2, then you will have type will remain 2 but order will change to 3. So you can have different combinations in your PLL, and it depends on the need of the PLL, what the PLL is supposed to do. We will change order and type of the PLL. By the way, type 2 and order 3 is most commonly used, and type is normally written in Romans. Type 2 order 3 is quite commonly used PLL. You will see why in the coming classes. Okay, any question with this? How we define type and order of the PLL? Normally you will find this in literature: type 2 order 3, type 2 order 2, or so on. Okay. Any question with this? Okay, so now we have depending on the loop filter, you can have different type and order, and depending on that you can find whether you are going to have a steady state phase error 0 or some finite value and so on. Okay, you can find all such things, right? Now a bigger question comes is, whatever we have done as an analysis, right, that analysis we did assuming that the PLL is actually locked, okay, is actually locked and it has all steady state and so on. But now let us come back to the real PLL when we start our system. So we have this mixer. So we will go through how a PLL locks actually. Okay, so we have a mixer based phase error detector, V in signal, then we have a loop filter, and let us say we are going to use a loop filter which is a low pass filter to begin with, which is like type 1 and order 2. We can think about multiple options are there, and then we have an oscillator. Okay, so and this actually is connected in closed loop feedback. You have V out and this is V in. So now I will write V in as, I will use amplitude of 1 sine omega n t, where omega n is equal to 100 mega or 1 gigaradians per second. This is just an example. Okay, and V out to begin with is equal to sine of omega naught t, where omega naught is equal to 990, or let me just say 0.99 gigaradians, which is the free running frequency per second, plus KVCO times VC. Okay, and at t equals 0, VC is equal to 0. We start our system at t equals 0. Okay, so this is how we are going to deal with it. Now, if you look at it, the mixer output, which is V error, we have to be pretty cautious about it. This V error is nothing but V in times V out. Okay, and V in times V out, we have done all this calculation. It turns out to be sine of omega in plus omega out. Okay, there is a change here. So omega in plus omega free, because these frequencies are fixed, plus KVCO times VC into dt 0 to t plus sine of omega in minus omega free, which is your let me just write that only, omega in minus omega free, which is the initial frequency error, minus KVCO. You can assume that, okay, I start just with a 0 phase offset to begin with, because these are all assumptions. So this is what you have at the beginning of your PLL. Now you see, if you look at V error in time domain, right? So this, I will write this term as omega in plus omega free times t plus another KVCO term, let me not write that, plus sine of delta omega 0 t minus KVCO times VC into dt. By the way, I should use here cosine, otherwise the terms are going to change. Okay, so this is what our V error is at the beginning of the PLL. And what do you see in this V error? If you just think about it, the signal is going to have, this particular V error is going to have two sine waves, one which is quite high frequency, which is going to be 2 gigahertz to begin with. Just think about it initially, what is going to happen. Let us assume that VC is very close to 0, right? At that time, delta omega 0 is 0.01 gigaradians per second, isn't it? This is delta omega 0, and at that time your omega in plus omega free is actually close to 2 gigaradians per second, exactly 1.99 or approximately 2 gigaradians per second. So you see the difference between these two frequency components, right? The magnitude may be same. Okay, so you see it is like 200 times the frequency. So if you have, just for example, you may have multiple ripples of 2 gigaradians per second, right? I cannot even plot that fast sine waves, right? At that time, this particular frequency component is 200 times slower, so you are going to have maybe extending to, you should have 200 cycles of 2 gigaradians per second with this sine wave. Okay, so that is how your V error is going to look like, okay, at the beginning with respect to time. Now, if that is the V error and it goes through a loop filter, right? So now let us assume that this loop filter is a low pass filter. So I am using this loop filter of omega, and this is with respect to omega, and this is having a sum filter bandwidth with a DC gain, right? Sum filter bandwidth, this is omega minus 3 dB bandwidth. So this particular filter is going to see two components, one which is sitting at 2 gigaradian per second and other which is sitting at 0.01 gigaradians per second. Normally, if we want to compensate for this frequency error, I should have the 0.01 gigaradian per second coming in the signal bandwidth, and this 2 gigaradians can be much away such that it is filtered out. Okay, so if you are going to look at VC, the control voltage at the output of the filter, that control voltage at the output of the filter will very much be like this, surely multiplied by whatever the DC gain is. If DC gain is 1, it will come as such. If it is not, then it will be different. Okay, so your VC is going to see the same sine wave as low frequency of the sine wave as you have at the V error node. Okay, does everyone understand that? Yes. Okay, so now for this particular V error, I can very well write that my V error is a V error is whatever you have seen, but V control is approximately equal to half of sine of, to begin with, by the way, sine of delta omega 0 times t minus kVco times whatever their control voltage, because we are changing the control voltage, so you can think about it, this is Vc times dt. Okay, or you can also write it as 1/2 of sine of whatever phase error you are having at that given instant of time. That will be your control voltage. Right? Now, how the frequency changes? See, we are looking step by step. We said, okay, you have initial frequency error. Now, that initial frequency error led to voltage error led to control voltage error. Phase error leads to control voltage, right? This control voltage is going to change the frequency, and how is frequency defined? Omega out is equal to omega free minus k VCO times VC. And what is VC? VC is nothing but k VCO times, if I just write from this equation, it is half of sine of phase error. So you see this complicated thing here. We start with the phase error, which is sinusoidal, that leads to the control voltage, which is sinusoidal here, which leads to the frequency here, right? Now, if I want to just write this final, your V out signal, right? V out is going to be sine of your omega free times t minus, plus, this is not minus, this is plus, times kVCO times Vc integral dt, and Vc is half of sine of phase error times dt. This is how your signals change. Okay, and if you are looking at your frequency is also changing in a sinusoidal manner. Okay, so in large scale system you do not see anything happening linearly which you have used so far in your small signal analysis. That was just giving you, okay, if I make a small disturbance, how the system is going to behave. Okay, so when we start our system, the bigger question is, if I have a certain frequency error, right, whether my system will lock or not. Right? If it locks, what will be the phase error, what will be the frequency error, or other control voltages which I will have? Okay, so these are all the questions which we have for our PLL in a large signal analysis. Okay, so normally a PLL output frequency, if you just start your PLL, right, you will observe that at t equals to 0, maybe without giving any initial condition, if you observe the frequency of the PLL, the frequency of a PLL may do all such kinds of things. Okay, so then it may have some kind of this, and then finally it may settle. This is how your omega out frequency may look like. Okay, and this omega out frequency, which you will see here, it is partitioned into different regions normally for our analysis, right? And then you can just say, yes, this is like, I will partition into different regions. This is with respect to time, okay, as soon as you start your PLL. So this is a specifically large signal. Your frequency is varying everywhere in the non-linear fashion. Okay, it's actually sinusoidal. Okay, and then this particular region is called a small signal region, and the last one is steady state, where your PLL has locked and you do not change the frequency, you do not change, the phase error has settled and everything has settled. Okay, so these three regions are normally defined. The analysis with the Laplace domain which we have done, that is your small signal analysis. Okay, and when we say I need to find the value at t tends to infinity, that is referring to your steady state value. Okay, and the thing is now, this whole is like this whole region going from whatever free running frequency and finally settling just before reaching the steady state, it comes under acquisition range of the frequencies. Okay, so let me, or not acquisition range, this is like acquisition of the desired frequency. So it is like you start your PLL, you give some input frequency and you have some free running frequency of the oscillator, right? And you just start your PLL till the time the output frequency or the PLL output reaches steady state. Okay, when it reaches the steady state, you say the PLL has acquired the lock, or the PLL has acquired the desired frequency. Okay, and then we need to define that how much range of frequencies can the PLL acquire. Okay, it may be that if I, for the above example, if I have only 0.01 gigaradian per second initial difference, it can only acquire that. But if I make it maybe 0.1 gigaradians per second, the PLL may not reach to this location at all. It may happen depending on how much frequency error and what loop filters and other things you have in the PLL. Maybe some particular crazy system will keep on doing this. There's no doubt. This is just like an example. It may keep on doing this. It may never reach to steady state. You can have all such sort of blocks. Okay, if such is the case, then you never acquire the lock. Okay, so depending on different blocks, you have these options. Okay, any question with this? Yes, guys, any thoughts that okay, why we are going to think about it or anything? By the way, there is no, it's like 40 minutes into the lecture, there are no chats even today, right? Yes, guys? Okay, so now what we have here is, see, what I have just told you, this is a very non-linear behavior. It is going through this multiple sinusoidal modulations and so on, right? So you define this PLL operation in terms of large signal, small signal and a steady state, and then you need to know, you need to find out that what is the range of frequencies the PLL can lock to. Okay, so then it comes under acquisition range. Okay, so this is different kind acquisition ranges are defined. Okay, and the first one is hold-in range. Okay, so here hold-in range is denoted by delta omega h. Okay, here the range of frequencies the PLL stay in lock. Okay, that's how it is defined. So the range of frequencies the PLL can stay in lock. What does it mean? It means that stay in lock. This is a technical definition for the hold-in range. So let us say I am having this particular PLL. Where does it go? PLL block. Okay, this PLL block. Okay, and just for example, you say that okay, my input frequency is 1 gigaradians per second. And my free running frequency of the oscillator is 10 megaradians per second. Okay, when I start my PLL. Now, when I start my PLL, if the PLL locks, then all the control voltages, voltage error, phase error, all these values will turn out to be in the negative feedback loop in such a way that my oscillator reaches the frequency of 1 gigaradian per second starting from 10 megaradians per second. Okay, that is the normal way a PLL can operate. Okay, that is one thing. The other thing is, let us say that V error and V control voltage on their own, they can never get those control voltages and phase errors. They can never get that. But if we interfere with the system externally, it's like some external interference, and we go and we make the system, we give those control voltages and error values and move out. Okay, so it's like, it is like this. You have a capacitor, and let us say there is a system which charges the capacitor, right? And the capacitor voltage at the best can go up to +1 volt, for example. Right? It can never go more than 1 volt. That is a limitation of this system. If it cannot charge an ideal capacitor more than 1 volt, right? But if I go externally and say, okay, I have a system, I am going to charge this to 2 volts, and then I back off. Back off means you disconnect yourself. So I charge this particular capacitor to +2 volt. And then this capacitor will hold a charge for 2 volts. This particular system is not going to take charge and reduce it to 1 volt. That is not going to happen. Okay. So it's like if I interfere with the system, if I give it the control voltage or the phase error which it desires, and the system remains stable at that point. How it reaches to this 2 volt is not important. It's like, the important part is it reaches, somehow it gets 2 volt and it remains there. No small disturbance to the system can change this +2 volt. Okay, it will remain stable. Such frequency ranges are called as hold-in range. Okay, the range of frequencies the PLL can stay in lock. How it reaches that lock is not a question here. It just locks somehow. Okay. Then the other range which is called is, all these are acquisition ranges, is called as lock-in range. Okay, what is this lock-in range? Lock-in range is the range of frequencies to which the PLL locks without any cycle slipping. Okay, I'll explain what do you mean by cycle slipping. So this is the range of frequencies. Okay, this is the range of frequencies the PLL locks without cycle slipping. Someone has posted a question. let me just go back, without cycle slipping. Okay, without cycle slipping means without the phase error exceeding 2 pi. So I'll just write it here, without phase error exceeding 2 pi. Okay, so here if you just look at the large scale, we will deal with these numbers specifically. So if you look at this large scale, right, you see that your basically your V error voltage is going as a sinusoidal, right, and the phase error is this value. This is your phase error. So if I want to write my phase error at any given instant of time is delta omega 0 times t minus kVco times V control dt. So when I say there is no cycle slipping, it means this particular phase during the process of locking, right, this particular phase error never exceeds 2 pi. It is bounded by 2 pi. And if during that time if the PLL locks, then that particular frequency is comes under lock-in range of the frequency. Okay. Then so wait a minute. This is the lock-in range, right? Yeah, that's a lock-in range. Then let me just pick up there is a question. So what's the question here? Hold-in range is defined around some nominal. No, it's not normally defined around some nominal value. Hold-in range is defined as okay, for a given oscillator and a given PLL, you will define what is the hold-in range of frequencies. Okay, it's nothing like it's not like an operating point. If you are referring to any operating point, no, it is not referring to any operating point. It is for a given PLL, you have an oscillator with free running frequency and then you define that. There are two things. So the whole thing is this. Hold-in range is defined as the range of frequencies the PLL can stay in lock, right? So it's just like all the frequencies at which the PLL is stable. Okay, how it reaches there is not a matter of concern. Okay, so it's like this. Let me just actually it will become more clear when we have an option here. So as I told you, let us you pick up an example and you say my free running frequency of the, just let's take this example. Let us say I am plotting omega in and omega out. Okay, and omega in is you can take it both the ways. So normally if you keep, let us say you start with omega in from some low value to some high value. Okay, this is your range of omega in. So if you change your omega in, then your omega out should also change accordingly, ideally, right? Now for some cases it may happen that if your omega in is, let us say omega in 1, if I have my omega in as omega in value as omega in 1, at that time my PLL itself on its own, whether it can or it cannot, I do not know, right? So I may have to interfere with the PLL and then it may get this particular omega out value. Okay, but if you pick up any point and if you have a PLL and if PLL input and output frequencies on this particular axis, on this particular line specifically, if anyhow you reach this omega out for a corresponding omega in, if you make a small disturbance, right, the PLL does not break. It's like the output frequency doesn't fall to 0 or it doesn't go to some higher frequency. That does not happen. It remains in lock for any small disturbance at the input frequency, whether it's a phase disturbance or a frequency disturbance or any disturbance, it remains there. It remains in lock. Okay, the thing which is not binding you here is how you reach there is not a question. Okay, you can reach anyway with external, internal, or so on. You just reach there, but you remain in lock. Does it clear that? Okay, so let me just give you an example. So let us say you have a sea level, right? And you have, from the sea level, you have a big mountain to climb, right? And you have a big mountain to climb, and then at the very top of the mountain, and it's a very steep slope or anything, at the very top of the mountain you may have some kind of a place like this, right, which is like a stable value when you are not, you can even sleep there, right, without falling. But if you are here, for example, if you sleep, you may fall down. So what we are telling about acquisition range is that so whether you reached, or whatever this frequency here, it's like all the frequency points, whether you reached to this particular point by climbing up the mountain and you reached there, or you came here by parachute or dropped down by airplane, whichever way it is, right? If you do any activity, you are stable within this point. You are not going to fall off the cliff from here. Okay? Acquisition hold in range even takes that into account. It's like all frequencies at which the PLL will remain in lock. How you reach there is not a matter of concern. Do you get that? Or it confused you more? What's the thing? Yes, Shubham? Okay. Then the other thing is, so lock-in range is the range of frequencies of PLL lock without cycle slipping. And as I told you, this is like without cycle slipping means without the phase error exceeding 2 pi. Okay. Similarly, you have pull-in range, which is like the range of frequencies, the PLL logs, range of frequencies, the PLL logs with or without cycle slipping. The PLL logs with or without cycle slipping. It is not at all constraint. Okay, so here your phase error can exceed 2 pi, and then also you can log, and this is normally by delta omega p. Okay, so if you just think about it, lock-in range is most constrained. You do not want to have any cycle slipping. Pull-in is relaxed, and hold-in is even more relaxed in the sense that, okay, no matter how you reach there, but once you have reached there, it's fine. Okay, so what we normally have is hold-in range is greater than equal to pull-in range is less than equal to delta omega lock-in range. And we will see these acquisition ranges for different kinds of PLL in the coming classes. Okay, so I will stop here. If you have any questions, let me know.